So far, we've talked about one main type of discrete probability distribution. The word distribution's in there because you have all these possible answers, right? It could be 0, 1, 2, 3, 4, whatever the problem happens to be, and the probability gets distributed over those answers, right? Some obviously get more than others because it depends on what the probability was. If the probability was that you were going to get a 1, well then obviously you're going to be closer to that, right? Or if the probability was better for towards the 4, you were going to do better. That was called a what type of distribution? What was that? The binomial. And the key for binomial is that there's two possibilities, right? And you know the probability, and then you are basically saying in binomial, I want to know exactly 3 of them got what they wanted, or there were 3 successes. Or you could use that cumulative distribution function that we learned about yesterday, and that would add up to whatever number you gave it. So if you wanted to add up the first, what's the possibility of 0, 1, and 2? Well, the easiest way to do that is to use the cumulative one, and it gives it to you. And if they say, what if it's more than 2? Well, you just use the complement idea. So that saves you a lot of time, that CDF, right? The PDF is the probability distribution function, which is why it's called the probability distribution. There are 2 more we're going to take a look at today. Geometric is one of them. It is discrete, obviously, that's why it's in this chapter. Okay? Distribution of a random variable x, again, x could be 0, 1, 2, who knows, depends on the problem, but it has to satisfy the following conditions. This, as you can see, has 3. I've obviously spread them out for you a little bit because some of you write bigger than others. The first one, a trial is repeated until a success occurs. Is that different than binomial? Quite a bit different, because we're saying, I want to know exactly 2 successes in binomial, right? I want to know exactly 2. Does it matter when they happen in binomial? No. If there's 5 trials, I want to know exactly 2 of them are successful. I don't care when they happen. I just want 2 of them to be successful, right? Here we're saying, I'm going to keep doing this until I get that success. So how many successes are we kind of really looking for? We're really looking for 1, the first one. Okay? So that's key for geometric. And so that one maybe we wanted to star or highlight or something along those lines, because that's the key distinction. It's very important that the repeated trials are independent of each other. I kind of think they didn't necessarily have to state that one, but I'll state it because the book I'm using did. Why didn't they necessarily have to state that? Yeah. Okay, so why did they have to state that you can't have the probability change? I don't think they had to. Yeah, because aren't we already told these are discrete? And isn't that one of the rules for it to be discrete? Yeah, so did they really have to state that? No, but I think they wanted to reiterate that because, let's face it, that was a couple sections ago that we talked about that, right? And the other one, the probability of success, again, P, is constant for each trial. Again, 2 and 3 kind of go hand in hand, really. And in essence, they really didn't need to tell us that because we already knew that because we're so smart. Because that's what discrete is. That kind of has to follow the rules, right? So the probability that the first success will occur on trial number X, so maybe it's the 3rd trial, maybe it's the 10th, maybe it's the 100th, who knows, can be found by the following very simple, really, formula. In fact, we've kind of used a portion of this formula before. So the probability of X, what's P again? And Q is failure. Okay. Now let's see if we can make some sense out of that formula. And where have you seen one similar to that? Yeah, binomial. What's the difference between this formula and binomial? Yeah, P's not taken to a power. Well, it is. But we know that power. How many successes do we want? So is the power really there? It is, and then we want all of these over here with the x minus 1 to fail, and is it always going to be 1 less? Yeah, because if it succeeds on the 4th trial, you're going to put P to the first, and how many failures are you going to have? 3. And see, on the 4th trial, 4 minus 1 is 3. So what else was in binomial that we don't have here? The combination out front. How come we don't need that here? I'm looking for one, and I want it in a very specific spot. I don't want to know how many ways can I get one success. I want the first success to be on, say, the third trial or the fourth. That's exactly where it has to be. You can't jumble it up. It has to be there. Okay, so this one, believe it or not, I think is even easier than the binomial because you don't have to figure out how you can jumble it up. You just say it has to happen there. And just a little note, in case you forgot, Q is obviously the complement of P. So I think this particular formula is actually easier, but does the calculator also have this on it? Of course it does. Okay. So you're a telemarketer, everybody's favorite person in the world. And from experience, you know that the probability that you will make a sale on any given telephone call is 0.23. So apparently you're very good at your job. Because when you call me, I just hang up. So you're basically a 23% chance that any particular given phone call will be a success. It's almost a quarter of the time. That's a pretty good telemarketer. Find the probability that your first sale on any given day will occur on the fourth call. So if we use the formula, so probability basically X is going to be replaced with, it could happen on the first call or the second call or the third call, right, or the fourth. It could happen on AM. The one I'm concerned with is the fourth call. Okay? And what you do is you take your probability of success, which in this case is 0.23. And are we really taking it to a power? We are, just to the first, right, because that's how many successes I want. I want just one. And then you take Q, which remember is 1 minus, because if that's success, failure is all the rest, which in this case is 0.77. And well, if I have one success and it's on the fourth call, how many have to fail? 3. This is just a streamlined version of how to calculate that. Okay. Would you expect it to be rather large? No, because would you expect it to almost happen kind of before there? When you have a 25% chance? You're kind of waiting until the end here, aren't you, with the fourth call to get your first success? Kind of, you know, especially with that probability. Again, there's no guarantee. This is probably what would happen, right? This is taking out of consideration maybe they're ornery in the morning and they only succeed in the afternoon, right? So, again, you have to kind of start pulling back from that. And I got something around there. Is that what you got? So 10.5% chance that it'll actually happen on the fourth call and not before that. Now really, you could look at this problem like this if you wanted to. And I think it helps you with the formula. Let's say first call, what do I want to have happen? Succeed or fail? I want to fail, right? Second call, fail. Third call, fourth call. You agree that's exactly what has to happen. Not that that success can be anywhere, right? That's that combination. That's when that comes in, that the success could be anywhere. Okay? And so basically, this is, isn't that exactly what we just did in the formula? So do you see how it streamlines it for you? But really, that's what you're doing. And you don't have to worry about that binomial of jumbling it up, because I don't want to know exactly one call being successful. I want to know the fourth call being successful. So can you make maybe a note of the difference between geometric and binomial? Are they very closely related? And some people confuse them a lot. And that's very easy to do. But maybe geometric, just say yourself, it's asking for a particular spot being successful. Okay, where binomial is saying how many ways could I be successful on just one of the 4 calls or something along those lines. What do you mean the catch? The catch is knowing the difference between this and binomial is the catch. So, of course, I told you this is actually on your calculator. So let's go ahead and turn that on. And I promise I will get there faster today. You probably saw this one already. So where would we expect to find this one? Yeah, distribution again, right? This is, again, do you understand the word distribution and why it's used here? All those probabilities are getting distributed over all the possible x values. That's why it's called the distribution. And obviously it's none of these, right? Here it is down here, right? Whoops, I went too far. Now there's 2 of them again, a PDF and a CDF. PDF is, the one I'm on now, E, right, is a probability distribution function. Is that what we're talking about right now? Yeah. What's the CDF again? Cumulative. That's the one that adds them up for you, which is really nice on those less than, greater than, that kind of problem, right? Now, what's the important information then in this problem? Do we know how many trials there were? You know what I mean? Do we know there was 20 times we checked into this? No, we just know that we want the success to be on the 4th. So basically in this problem, we know x is 4, right? That's the one I'm concerned about. What else do we know that's important? Probability of success is 0.23, right? And do you agree that's pretty much the only two things I really need to know, and know it's geometric. If you know that, we're good. So what do you suppose they're going to ask you to type in first, based on what you've seen? No. Probability, 0.23. And make a note of this off to the side somewhere, of how to type this stuff in. If I remember correctly, I think always the last thing they ask you for is x. If I remember on these distributions.
Last time we did MPX.
Yep, MPX. So I think basically x is always last. So, and we know x in this case is just 4. Let's face it, on this one, wasn't it easier just to kind of, by the time we got into this thing, it was easier just to do the problem. But hopefully we get the same answer. And we do. Because I want to show you what's out there. So, any questions on that? So let's try that next one then. Don't we have another one on there? So find the probability that your first sale will occur on the 2nd or 3rd call. Lots of ways you could do that. You could use the CDF. I think with how these problems go, that probably might take too long because you're still going to have to subtract some stuff. Because I'm not saying 1st, 2nd, or 3rd. I'm saying 2nd or 3rd. Agreed? So what you do, remember 2nd or 3rd, when that or was in there with probabilities, what did we do? We added. When it was and, we multiplied, right? So or means kind of add in statistics. So what we have to find is basically P of 2, and then we have to find P of 3, and then we're going to take those two answers and add them up. Now, you could be, here's kind of how I look at the problem. Here's how I would do it, just because of what I have on my calculator right now. Do you agree I have the correct stuff kind of on my calculator right now? Right? So hit 2nd, enter, it'll bring that all back and let you edit it. Okay, and just go back and change the 4 to a 2, right? That's the nice, so 2nd enter always does that for you. You probably could just go ahead and do plus, but I'm just going to hit enter and then bring 2nd enter again and bring the other answer up and then just add them. Let's find out. This will be fun. Ooh, I don't know if that's going to work, is it? Let's try it. Plus. Nope. Didn't like that. I don't even know what that is. Yeah, where's that from? Uh-oh. Now we're in trouble. Oh, well. That's okay. We'll just do it by hand then. It was a good thing to try. It didn't work. So probability of 2, let's face it, what's our success is 0.23, and how many of them do I want? If this is geometric, I want 1 success. And let's face it, if there's only 2 total, the other one has to fail, right? You with me on that? Then over here, we got 0.23, again, to the first, and 0.77 to the second, because I need 2 to fail, correct? Again, you could look at it this way, that this truly P of 2 would be a fail on the first one and a success, right? You see how they kind of write them different, but that's because they always know that first one. They always want to put P in front, okay? Here is fail, fail, succeed. Now, mathematically, that's not all that hard to type into a calculator. So we got 0.23 basically times 0.77, which I got 0.1771-ish. Whoops. So 17% chance. I believe that because, again, we got a 23% chance that this is going to happen on each call, right? So 17% chance of that happening. And then over here it's saying I got about 0.136-ish, right? Again, where you round is kind of up to you on these unless I specify. And so you add them together and you get something. So you take this answer, add that answer, because that's 2 or 3, and you get about 0.313-ish, right? Somewhere in there. You agree with that? Okay. So 31.3% chance on 2nd or 3rd call. Believable? It does, but remember, it has to get distributed over all the possibilities. Well, not necessarily over 4. Could we ask what's the probability of it happening on the 10th call? Do you agree that that would be very low? So do we have to take the 100th call into consideration in this distribution? Yeah, the answer to that particular is very small, correct? But we have to take them all into consideration, and once we get them all, they have to add up to 1. So you see what I mean? The distribution thing is a very important idea to have. Yes? Yes. Mm-hmm. Okay, so what do you think that would mean? So you had a 4 in place of, okay. I don't think so, because you see how they are different answers. 0.1771 and 0.105, so I don't think you had the 4 in the place. Okay. Is it possible that something like that could happen? Yeah, but the probability would probably need to be half for the distribution to work out that way. Okay. Was there another question? No? Okay. So that's geometric. So make some kind of note somewhere that'll help you out there. So what type of problem could I give you here where that cumulative distribution function would come in handy? Geometric and cumulative. Well, it can't happen on both. Your first success can't be on the second and third call. Yeah, you could say first or second or third, right? It's taking all of them into consideration. Obviously, 0th call here doesn't make any sense, right? So you could use the cumulative if you said first, second, or third, or maybe, first, second, third, or fourth. It all depends on how far they want to go. And then a cumulative will just add them up for you. Okay? Or they could say on one of the first 4 calls or something along those lines. Okay? So any questions on that? So that's geometric. Poisson. Okay? The formula is, the concept not really, it's a discrete probability distribution of a random variable that satisfies the following conditions. So again, it's discrete. So we know the probability kind of has to hang in there for us, right? It has to be independent. We know a lot of those things. And you can paraphrase this first one, obviously. The experiment has to have basically counting the number of times that some event will occur on some interval. That interval could be time, area, volume, whatever. I think you're mostly going to get time. The example you have here is going to be time, which might get you to maybe confuse this with continuous. Remember discrete versus continuous? But we're not saying everything within that interval has to be included. Okay, so that's why. Because x is still how many would happen. So either there's 0, 1, 2, 3, or 4. You see what I mean? It's not like you can have 1.2 of some event. So that's when continuous would come into play. Here it's 0, 1, 2, 3. On some given interval, again, time. Like it could be per year. That's an interval, right? Okay. And one we should already know. The probability should be the same for each trial. Again, that's just discrete. That's just a probability distribution. We don't really need to worry about that. And again, the independence idea. Basically, you can just say independence and kind of boils down to the same thing. But again, 2 and 3, we should already kind of have that under our belt. Again, yeah, this formula is considerably more difficult than the last one. It's a good thing the calculator can do it for. I'll show you kind of the first one more of a kind of by hand, and then we'll look at the other one maybe using the calculator. Everybody ready for the formula? Mu to the x power, e, which for those of you that do not know is a number. It comes kind of from the natural log, and it is, as you see there, approximately 2.71828, blah, 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 keeps going. All right, but your calculator has that number for you, so you don't have to do that. So it's e to the negative mu all over x factorial. And for some of you, yes, I could just put the e to the mu on the bottom, make it happy, but this formula likes to put it on the top, so that's where we'll leave it. Yeah, it's mu to the x Ooh, I didn't like that very much, did it? So mu to the x times e to the negative mu all over x factorial. E is always 2.7182, yes. It occurs in nature a lot. And there's a lot of ways of defining E.
Random events.
Mm-hmm. Growth, decay, where leaves end up on a branch. No, that's phi. Wrong one. All right. So let's remember that we got mu. Remember, mu stands for what again? Yeah, the average, the mean. X here is your random variable, so that's how many occurrences we want. Maybe it's 10, maybe it's 2, who knows? And E is E. That's about all we need. So let's do kind of this first one here more by hand, and then we'll use, like, we're using the calculator, but using the formula, and then we'll let the calculator, because obviously you saw Poisson, we were just in there. You saw it. It was one of them. The mean number of accidents per month at a certain intersection is 3. So there's an intersection in some town that has an average of 3 accidents per month. Is that an interval of time? But are we still just counting? There's 1, 2, 3, or 4 accidents, right? There's not, we're not going to do, anything like that. So what's the probability that in any given month 4 accidents will occur at that intersection? Do you think that probability is pretty high? The average is 3 per month. Chance of having 4. Realize you got, different number of days, but we have the mean, so we don't need to know how many days there are. Well, let's find out. So the probability of x, so it's the probability of, in this case, our x is 4, right? Because what I want to know about is 4, is you have to take the mean, which is 3, to x, which is 4, and then e is just e, to the negative mu, so the negative third power, all over x factorial. So I'm going to write that over on the whiteboard so that when I go to the calculator, I can still see that. Right? Do you agree with that? So let's go ahead and see what that calculator says for us. So again, we're not going to use that distribution. We're just going to take 3 caret, right? That's how you get it to the 4th power, this one right here. 4th. See the carets right there? You don't have to do times. Where's E? Yeah, it's on natural log. So everybody look up here for where E is. Right above natural log there, you see e to the x power, right? Right above the net ln. There's an e right there. So how do you get that way? You have to hit second and then e. So there's e. It's in there for you. To the negative third, be careful with your negative. Use this little one here. Okay? Negative third. Now, something very important has to be done next. Yeah, you got to close that thing off. Now, you could hit enter and then go ahead and divide by 4 factorial. A lot of times you might want to be careful, but that's multiplication up there, and this knows order of operations. So that's what it's going to do first anyway. And so then divide by 4 factorial. So you have to hit the 4 first, and where is factorial? You could just do, yeah, it's under math. And you got to go over to probability. Everybody with me or no? Am I going too fast? And there it is, number 4, right? So you scroll down or whatever it is you like to do. There it is. Factorial. So is that typed in correct? 3 to the 4th, e to the negative third, divided by 4 factorial. And enter. Are you surprised by that?
Yeah.
I'm a little bit too, but it is right. Yeah, I think 100 accidents probably, again, could be pretty small, right? But you have to realize that that distribution has to take care of that number too. And obviously that's going to be very small, right? You got to think of it all being distributed in like bars. Think of all these bars on there, and they all have to be taken care of. And so that's why some of these may be smaller than you think, because it has to take all of them into consideration. Obviously, what's going to be your best is if you asked it if there were going to be 3, right? That's going to be your best answer. But is there any guarantee that that's going to be a whole lot higher in this one? Not really. Yes? It'll be just a little bit off. For me, the question there is if you type in the number for E instead of using the E, that's fine with me, but it's right there, so you might as well just use it. It's got that number for us all the way out as far as it goes. Because the calculator actually does a big long series of numbers to do E. Because that's what it is. It's a sum of an infinite series. And so that's how the calculator does it. Because all these calculators can do is add and subtract. They're just told how by programs. They're told how to multiply and do all this stuff by programs, by adding and subtracting. So
They just do the long version of it.
pretty much, they do a very long version of it, and they, let's face it, they do it very quickly. Okay. Yes, writing those programs is awesome. So let's go ahead and find out how we're going to do that other problem, because example 2 has another answer, right? It has, so that's the answer for 4 accidents. Now we want to know what's the probability of 4 or 5. Well, we already know this answer, right? This was what, 0.168, something like that? So now what we have to do is probability of 5, and you could do it again the same way, right? But let's go ahead and let Poisson and the calculator do that for us, if that's all right with you. So here's our, whoops, wrong one. Distribution. You got to go to Poisson. Do I want it to accumulate it or probability? Yeah, probability distribution. So you want letter C there. So Poisson. And so you hit that. Now, what do you suppose are important bits of information? Because we're talking about a different thing here. So in the formula, what are really the 2 things you need? E is kind of its own little deal, right? But what are the only 2 other things in that formula? Mu and x. That's it. That's all you got to know. Do we know them both? Yeah, mu is going to come first. Very good. And in this problem, mu is 3, comma, because x almost always comes last. And x in this one is 4. But don't we want to know about 5? We already did 4. We already know that answer. So you can do it again. It's going to come out to the same number, but we might as well just go get 5. Do you expect it to be higher or lower than that number that we have above there? Well, 16.8% for that top one. Should it be less or more? Why less? Further from the mean, right? We have to distribute all those values, and it's further from the mean. And I'd say that's believable, huh? Got less, right? All we need to know here is the mean, and we already have the answer for 4. That's why I didn't do it. There's the answer for 5. So is this 10% here, 10.1%, is that the answer to the actual problem? It says 4 or 5. You got to add them. So the nice thing here is if you didn't want to round, we could just go ahead and say add, and then go 0.16803, and I'm tired, so I'm done. So 26.9% chance that it's either 4 or 5 accidents. Right? Believable. And just out of curiosity, that's the answer, by the way. I gotta know. I gotta know that answer. Could you agree that should be the highest probability? And if 4 was only 16.8, what's this one going to be? Now, why is that so low? Because, again, they have to distribute that over all possibilities. It's still going to be the highest, exactly. You put in 2, it's going to be lower again. Okay, and you're starting to get that idea of, and I'm trying to give you this little arch as a look, that where the mean is, obviously, is where you're going to get your best result. Is there any guarantee that it's going to be a good result? No, because remember, do they have to consider 1,000 accidents in this intersection? Is the probability very high there? But does it take away from this number? That's because your total can only be 1. Okay, so it takes away from you. And of course, if you were going to use the cumulative, so let's just type in, we know the mean is 3, and let's type in, I'll just type in a 4. So what is that going to tell me? If I hit enter, what's this answer going to mean? Again, forget the sum done. So 0 accidents, 1, 2, 3, and what's it going to do to them? Add them up. Okay. So let's face it, with the number we're trying, this is probably going to be pretty good because the mean's in there, right? You think it's above 50%? Yeah. I would assume that it is.
Oh, yeah. Even 1%.
Yeah. So, what's that? Put a 5 and then it'll be bigger? Yeah, because it's adding them up. It's adding more, exactly. Okay. So, I think you get to 100 pretty quick, pretty close to 100 pretty quick, I would guess. Oh, you'd be, I think it might even have a problem. It might not even be able to do that. Because you'd be doing 100 factorial. You know what I mean? That's me looking back to the formula.
You can do it now.
Okay, so,
It's up there.
yeah, it's going to have some trouble once you get big. So,
It's going to say overflow.
any questions on any of what we covered today? I think the biggest thing for you to do tonight, no homework tonight other than try and make sure you know the difference between binomial, geometric, and Poisson. Know the difference, maybe know what do you need and what does it tell me. And keep in mind, I think it's huge to keep in mind that you are taking some bit of information and you got all these bars that are all over the place. All right, and I mean, isn't that kind of what this one would look like, something like that? You're distributing 1 over all of that. And so that's why some of these are probably lower than you think because of all of this out here. Okay. It takes up a lot of information out there. Even if it's really, really tiny for each one of them, there's a lot of them. Okay? And so we have to kind of take that into consideration as we're looking at this. Because, of course, we're going to try and have it trend towards that. Yeah, they put a stoplight or perhaps a roundabout. That's everybody's favorite now.